Hello, algebra. So we're talking about exponential decay again today. And the whole point of exponential decay is that it gets smaller. We've been talking about growth, that gets bigger. Decay gets smaller. All right. First thing I want you to do is make sure you have all the stuff you need. I want you to have paper. I want you to have pencil. I want you to have your phone nearby with your Desmos apps downloaded to them. So you are ready to go. Pause the video and get ready. Okay, if you're back, that means you are ready. You have it all. And you're looking at these shapes and you're like, what are those shapes for? Well, remember that old rule of 4? Any function can be considered or thought about or described using 4 different lenses. What are those 4 different ways that we think about functions? Write them down on your paper. Pause the video. Okay, we're back. And we're back. That means you have written as many of these as you can remember. Perhaps you're thinking, oh, graph. I could graph a function, or I could write an equation for a function. Or maybe you're thinking of a table of values. Or what's that last one? Written description. And if you're like, but Miss Miller, you're putting them in the wrong places. That's okay. They're all equal. They can go anywhere they want. All right, now we are going to think about exponential decay today through each one of these lenses. And let's start with table of values. So, table of values. Now, a lot of times people are like, well, first maybe you're thinking, wait, this table is going up and down instead of left to right. That's okay. We can make our table up and down, left to right, your choice. And so let's say a lot of you guys are like, you have to start at -1. You can start wherever you want. I am even going to start right here. I'm going to go 0, 1, 2, 3. Let's just start there. Now I'm going to take a function, pretty standard function, y equals 1/2 to the x power. So maybe I don't even tell you what the function is. Let that be a mystery. Forget what I just said. And what if I tell you that this is 1, and from 1 we go to 1/2, and from 1/2 we go to 1/4, and from 1/4 we go to 1/8. Perhaps you recognize these numbers, or maybe you recognize the denominators of the numbers, 2, 4, 8. You're like, that sounds familiar. That seems very much like an exponential growth function I know about. I'm going to write it in a different color. We'll use green to symbolize growth. That really reminds me of y equals 2 to the x power. Now, I know 2 to the x power goes, 1, 2, 4, 8, 16, and so on. That kind of is reminiscent of that. And you're thinking to yourself, what number, how do I go from 1 to 1/2, from 1/2 to 1/4, from 1/4 to 1/8? And perhaps you notice, well, I divide by 2 each time. And to that I would say, excellent observation. We want to think about this as multiplication, though. So how would we change divide by 2 to a multiplication problem? And I think it was Mario that said, you do it with fractions. So multiplying by 1/2 is the same as dividing by 2, cutting it into 2 pieces. So as I get bigger, as I go down 0, 1, 2, 3, I multiply by 1/2. So how will I go back up? What number times 1/2 equals 1? Well, 2. Half of 2 is 1. And what number times 1/2 is 2? Half of what number is 2? 4. And maybe you start to notice, oh, look at that. She's just multiplying those numbers by 2, right? As I go up the table, I multiply by 2, so this will be 8. And there's this really beautiful symmetry here, right? 2, 4, 8, 2, 4, 8. It just is nice. Maybe it's so nice that you're thinking, I want to graph it. I want to graph these numbers. Let me plot these points. Okay, we can do that. Here we go. Make your little table, or your XY coordinate plane. So this is X, this is Y. Let's put some arrows on there. Okay, now when I'm going to plot these points, I'm going to go all the way to up to 8. So I'm going to go, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Notice I don't have any negative values in my y's, so I don't need to have any negative values in my y's down here. All right, so I had over 0 up 1. I had over 1 up 1/2, 1/4, 1/8. That becomes very difficult to graph. But if I go back, I go up 2. If I go back 2, I go up 4. 1, 2, 3, 4. If I go back 3, I go up 8. And do you see that pretty curve that's starting to form? Oh, it's so pretty. I love it so much. I've got my exponential growth curve, but it's just reflected across the y-axis. It looks exactly the same. It's gorgeous. It's just a mirror image. I also have, do you guys remember what this funny name is called? That thing? We have an asymptote right along the line y equals 0, an asymptote. Okay. Now, let's talk about the equation for this baby. We are multiplying by 2 constantly, times 2, times 2, times 2, times 2. And remember that exponentiation is a shortcut for repeated addition. So I could say 1/2 times 1/2 times 1/2 times 1/2 times 1/2. I could say that, or I could say 1/2 to the 5th power, because there are 5 1/2s. And since this is just repeated multiplication, 1/2 times 1/2 times 1/2 times 1/2, I can think about it in the exact same way. Now, exponential decay equations are going to be in the same form, y equals a times b to the x, as our exponential growth functions. A is still the initial value, but b is not the growth factor. B is the decay factor. And you're probably wondering, well, how do we make it be decay? Why? How? Well, it has to do with b being between 0 and 1. When we have a fraction that's between 0 and 1 and we multiply it by another number, that number gets smaller. And remember, decay is all about things getting smaller. So remember when I wrote the equation up here and then I was like, no, I changed my mind. I don't want to write the equation over there. Well, we have. Now we can. Remember, our initial value here is 1. So our function is going to be y equals 1 times 1/2 to the x power. Sometimes you will see people just write y equals 1/2 to the x power, because remember, once you multiply it, you do your exponents first. Then you multiply that number by 1. Well, it's the same as that number. But I like doing this. It's helpful. Okay, now let's talk about exponential decay situations, because this is really where a lot of the good stuff happens. So Where do we see this in the real world? Well, here are some examples. Have you ever noticed that you get a piping hot cup of coffee or tea or hot chocolate and it cools really fast? Like you get it and it's warm, it's too hot to drink, and it starts to cool really fast. And if you miss it, like, oh man, now it's too cold to drink. But then it kind of just flattens out. It just stays that temperature for a long time. Well, it's approaching room temperature. Exponential decay. How about how fast water evaporates? Have you ever been on like one of those log rides at like an amusement park? You know, Splash Mountain at Disneyland. I don't know what it's called at Great America, but you go and it's a hot day and you go on the log ride and you get soaking wet and it's kind of fun. But then like immediately your jeans start cooling really quickly. Evaporating. The water dries off really fast and you're like, I'm hot again. But then it gets late, the sun goes down, and like it's nighttime and your jeans are still wet and it's very annoying. Exponential decay. We're going to focus a lot today on how material objects depreciate in value, so like a car or an iPhone or whatever. But some other ones, like how much of a certain drug is left in your bloodstream. So let's say you're a doctor, pharmacist, anesthesiologist, and you need to calculate, you need to make sure that somebody is not taking too much of a certain drug. So you have to figure out how much time they have until they can take their next pill, or perhaps maybe how much time they need between taking the pill and when they can drive, if it's like a sleeping pill. So this exponential decay is valuable there. And then, maybe you are doing some carbon dating, finding out how much carbon 14 there is versus how much carbon 12. Well, that's an exponential decay problem as well. All right, so let's talk about cars depreciating. So here we go. A car depreciates at 20% per year and costs $20,000 new. How much is the car worth in 10 years? Okay, so 10 years is kind of a long time, but not that long in the lifespan of a car. So we've got depreciates at 20% per year. Every year it's worth 20% less than it was the year before. And it costs $20,000 new. All right, let's think about this. Now, I bet you already know our initial amount. How much does that car start out at? It starts out at $20,000. Our initial amount, A equals $20,000. Easy peasy, lemon squeezy. But our decay factor is more of a challenge. That's B, right? Now, B, just like when we were doing exponential growth problems, we have to do a little bit of work to get B. So remember that B equals 1 plus R, and you're like, R, the rate of growth, in this case, the rate of decay. Okay, our car depreciates at 20% per year. That means it decays at 20% per year. Our rate of decay is negative 20%. We're losing 20% of the value, so that's a negative. Now, if we transform this percent into a decimal, we would say the rate is equal to negative 0.20, right? We move the decimal place 2 places. And now, when we plug this into this formula, B equals 1 minus or plus negative 0.2, that would mean B would equal 8. Our decay factor is 0.8 or 80%. Or think of it this way, our car holds 80% of its value. It depreciates at 20% per year, but it holds 80% of its value. So we've got A, we've got B. Let's do some math with this. Now, technically, we could do a table of values. So let's just see what happens when we do that. X, Y. And I'm going to do a long table because I have a long slide. So at year 0, I buy the car new. I drive it off the lot. It's worth $20,000. But a year goes by and it loses 20% of its value, or in another case, it holds 20% of its value. So, holds 80%. So we have $20,000 times 0.8. So in 1 year, it is now only worth $16,000. It has lost $4,000 of its value, just like that. Whoa. But another year goes by, and now what I'm looking at is that 16,000 times 0.8. So now it's only worth 80% of that value from the year before. So now it's worth $12,800. It didn't lose $4,000. This time it lost $3,200. Let me just make sure I got that. Yep, $3,200. So it lost less this time. And if we were to find out after 3 years, what would it be? Well, we're going to take that number, that 12,800, and multiply that by 0.8. And we get 10,240. So now $10,240. So in 3 years, our car's almost lost half of its value. That's kind of crazy. But when we consider this graphically, what happens is we start out here at $20,000. And after 1 year, 2 year, 3 years, here's about half. We've lost half of its value in just, 3 years. That's kind of tough. But what happens at 4, 5, 6, 7, 8, 9, 10? Well, what happens is we have this big loss here, but then our loss kind of flattens out. So we still lose money, but not so much. The price differential between a 1-year-old car and a 3-year-old car, that's a big loss. The price differential between a 10-year-old car and a 12-year-old car, not that much. So that's what it looks like as a graph. If you want to, you can go to Desmos and graph it. Here it is. And I changed the X and Y, changed the window so we could see, here's the X axis, and I put it from 0 to 20, and I changed the Y axis from 0 to, and I put it up at 25,000 because I was like, I like to see a little bit above. All right, so then when we look at it, it's like, oh, there's that graph, right? And if you ever want to export a graph, see this little rectangle, you just hit that. You can copy the link. If you're doing it on your computer, you'll see a little thing where it says, you can save it on there. Okay, fun. Back here. That's what it looks like as a graph. All right, as an equation, do you notice that we have this repeated multiplication every time we take this number, we multiply it by 0.8, multiply it by 0.8, multiply it by 0.8, and that we get this we're repeating this over and over and over again to the next value, 0.8. And so we can use an exponent. We can say this is y equals $20,000 times our decay factor, 0.8, to the x power. And if I want to know how much it's worth in 10 years, I could multiply 0.8 10 times, or I can, I've only done it 3 here. If I do it 7 more, I might make a mistake. Instead, I can say $20,000 times 0.8 to the 10th power, and it's going to do that math for me. $2,147.40. $1,246.48. So not Canvas. In 10 years, it will be worth $2,147.48. Okay? I can tell you my last car that I had, I traded it in at a dealership. Do you know what they offered me for the car? $100. The dealer was so worried. He was like, I don't want to offend you. And I'm like, don't tell me it's negative. Because that wouldn't work because we have an asymptote here. So even though my car was very old and not running very well, I still got $100 in trade-in. All right, now it is your turn. I want you to let me know some information about this. An iPhone costs $400 new. This was in a world when iPhones cost, I wrote this problem, several years ago when iPhones were only $400 new, and they depreciate at 60% per year. I want you to pause the video and work through this problem. Use this example up here to help you. You can think of it as an equation. You can think of it as a table of values. You can think of it as a graph. I have given you the written situation, and you now have a choice of how you're going to think about it. And I want to know, how much will it be worth in 5 years? So this is part A. And part B of the question is, will it ever be worth a negative amount of money? Will you have to pay someone to take an old iPhone off of your hands? Okay, and this is question 1 of your homework. So you're taking notes, you're doing this problem, question 1 of your homework. Your homework is also to show me all these notes. So if you haven't been taking notes, buddy, restart and start taking notes. My dear, what have you been doing? Okay, so question 1, an iPhone costs $400 new and depreciates at 60% per year. How much will it be worth in 5 years? And will it ever be negative? Okay, can the value ever be negative? Those are your 2 questions there. Now, this is already shaking up to be a long video, so we're going to skip some of this, and we are going to go to this question. This was the question that a lot of you were asking me about over email, and you're like, please, can we talk about this? This is the one I don't get. Okay, we will talk about it, and you will have a better understanding of this, and you will write some stuff up here for question number 2 of your homework. All right, and then you're going to send it to me. All right, the NCAA Basketball Championships, also known as March Madness, uses brackets to determine which teams play each other. If a team wins, they advance to the next bracket. So let's just look at, here's a visual of this, and we can zoom in. You can see this is 2019 because they didn't play this year because of Corona. All right, so like we have these brackets, and then this group ends up playing this group, and right, and they all eventually get down to one team. So let's just look at this in a little more detail. So let's see here. We have Duke plays North Dakota. Duke wins. All right, then Duke plays UCF. Duke wins. Duke was the number 1 seeded team. Then Duke goes up against, this bracket here. Let's see. LSU advances. LSU plays Michigan. Michigan advances. Duke and Michigan are the number 1 and 2 seeded teams. LSU was 3. So we can see who's going to win? Well, Michigan wins. And now Duke was number 1 is out. Okay, and then Michigan goes to play Texas Tech. Texas Tech wins. Then from over here, this whole side, Virginia advances. They play each other. Virginia wins. So that's kind of how brackets work. And let's look at the math of it. The champion starts with 64 teams. At the end of the first round, there are 32 teams. At the end of the second round, there are 16 teams. At the end of the third round, there are 8 teams. Now, the first part, the thing I asked you was like, what could we ask? If you were the math teacher, what would you ask? If you're a basketball player, what do you want to know? All right? So the first thing I want you to do, because this just really feels very table-y to me. It really makes me feel like, oh, I should be writing this down in a table. The first thing I want you to do for your homework is to create a table of values. Maybe you did this on Friday. I want you to do it again. Just after seeing this lesson, how do you think about it? So step 1 is to create a table of values. Step 2, I want to know, can you come up with, and I'm going to say with the table of values, extend it as far as it makes sense to extend it. Like, we're going to have one winner, and then after Virginia wins, they stop playing, at least for a year. So create a table of values in what we call a reasonable domain. So don't have it be go negative. That would be weird. Okay, so create a table of values. And then the next thing I want you to do is see, can you determine the function? Well, actually, that's a yes or no question. Some of you are going to be like, yes, I can. And some of you are going to be like, no, I cannot. I don't want you to do that. I would just want you to determine the function. Let's start that over again. Determine the function. Let me fix this. Values. Okay. So you are going to create a table of values for your March Madness function problem, and then you are going to determine the function. Okay. So let me just review. What is it that your homework is? What are you turning in tonight? You are turning in a photo. Oops. It is getting late here. You are turning in one file that is multiple pages, a PDF even, that would be tops. One file that is multiple pages. You can use an app like Genius Scan. It will help you do it. It will email the entire thing to you. You upload it to Canvas as a single file. It is beautiful. Okay. I wonder if you can even upload it directly from Genius Scan. I wouldn't be surprised. So this is an app. You can get it in the App Store or whatever, whatever it is, whatever the Galaxy equivalent. I don't know. I can't speak. Okay, it's late. Anyhow, PDF Genius Scan. You're going to turn in one page of notes, multiple pages of notes in one PDF. You are going to have 3 things. You are going to have the notes from today's video. You're watching this today. You are answering the question about the iPhone. So we have the iPhone problem in 2 parts. What were the 2 parts? The 2 parts were, how much is it worth in 5 years? I forget how many years. 5 years, 4 years? How much would you pay for a 5-year-old iPhone? Not much. 5 years. Okay. How much is it worth in 5 years? And B, can the value ever be negative? Part 3 is our March Madness question, our basketball brackets. Okay, and here is part A, is write a table of values in a reasonable domain. Go all the way down till Virginia wins. And then B, you write a table of values and then you determine, what did I ask? The function. What is the function for this? All right, 3 things. Your notes, the iPhone problem, the March Madness problem. Please, 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 please upload this as a single PDF of multiple pages. All right, guys.